This is a little demo to help show the effects for Gaussian illumination and setting the telecentric condition for a particular lens. So this is a list of what we're going to do. There's a starting point lens. We'll turn the telecentric condition on. We'll change the apodization. We'll use an option called geometric image analysis to more accurately look at the illumination at the lens to check that we're modeling this thing correctly, and then we're going to go through some variations of that. So here's the starting lens. It's pretty simple. It's something close to 25 millimeter focal length. You can take a look at this and create this own lens for your system. Front radius is 25. Its biconvex back is 25. And the distance from the object to the first surface of the lens, which is also the stop, I've set at 50 millimeters. None of these parameters are particularly important. We're just going to sort of show some of the general effects. So I start with uniform apodization. This is probably the default if you bring in a new lens. I've changed the object space NA to a value of 0.1, and in particular you can't use entrance pupil diameter. We're going to have the telecentric off usually when you first start up, so that's the sort of lens you should see. There's also a field height set in this lens, and it's not shown in this layout, but if I turn it on like that, I get that. So field height's a couple millimeters here. Distance is, what did I say, 50 millimeters from the object to the lens. And if you haven't done so, it's good to turn this active cursor on, and as you run the mouse around, you can measure the distances. So this is probably the standard lens that you'll first land at if you set up using the defaults. So let's start changing the apodization and see what the effects are. So we go from uniform to Gaussian. The default is 1. When I update here, I'm going to turn off the second field point rays to make this a little more clear. But what you can see here is that Zmax has changed the rays from uniform spacing to such that they're weighted a little bit more in the middle. And that's to emphasize that it's a Gaussian, so you have more energy in the middle and less on the outside. If you change this apodization to 2, refresh, does it more extremely, but at this point it's a little bit hard to tell from a quantitative point of view. So what we'd really like to get is a more quantitative way for looking at that. And there aren't that many options to do that particular task in Zmax, but we're going to choose one of them, and it's called a geometric image analysis. So we go back here, we're on the Analyze tab, Extended Scene Analysis, Geometric Image Analysis. So what geometric image analysis is going to do is, I open up the settings files, it's going to trace a bunch of rays from a file, and the file has certain pixels that are turned on and off. And the file that I've chosen from the drop-down list is circle.ima, and there's a reason for that. So what circle.ima is a text file with a bunch of zeros and ones. So Zmax is going to trace rays from every pixel that's defined by a 1, and it's not going to trace any from pixels that are defined by a 0. So at the object plane, it's going to trace these rays defined by the circle.ima file. So it's basically going to mimic a circular source, okay? And the size of the circular source is defined by this field size, which we're going to set very small, because what I want to do is make this thing a point source. So it's going to trace rays from this circle defined by the IMA file, but it's all going to start with some scale such that it sits within a 0.001 millimeter diameter circle. So here are some other IMA files that this is a cross, right? It's only 20 pixels in each direction. Here's a row of ones right in the middle. Here's a 1 in the middle column all the way down. So you could take this thing and use this to simulate how it would image across through the system. But again, because the circle matches up with some later geometry that we're going to use, we're going to stick with the circle. So it takes this circle.ima file, it plops it at a particular field position. In our case, we want to use it on axis to start things off. It's going to trace rays, and we're going to look at it with a plane that is the size of the image size. And the place where we're going to look at it is not at the image, which is often the default, but I want to look at it at this. Surface 2 is the front of the lens. And the way we're going to look at it, the show method, is going to be false color. It's a 2D plot. So we have circle.ima file. It's very small. Excuse me. It's being done at the first field point. We hit OK. And we get this thing that looks sort of like a Gaussian, right? It's red and hot in the middle, less intensity off to the edges. So this is useful, but it's still not very quantitative. So we go back to the settings, go to cross X. Okay, this is getting more useful. Change the line thickness from thinnest to standard. And so now what we see is this Gaussian apodization. Okay, so this is the bottom axis is the X position in millimeters, and the surface is defined over here in the lower left, so you know you're at surface 2. And the vertical axis is the irradiance, watts per millimeter squared. So it's giving an indication of the Gaussian apodization. So if I change this back to 1.0 from 1, I hit refresh. All right, and I have the auto cursor turned on. Active cursor. I can read out these values. So this is about 0.040, 0.030. It's about 13.3%, which makes sense, right? If the amplitude is down by 1, the intensity is down by e to the minus 2, and so that's 13%. So I've described the IMA files. I'm not sure that I showed where the IMA file is located. You need to know that if you want to look up your own. So settings, edit this thing, save as. It's in the ZMAX folder. There's another subfolder called IMA files, and the various IMA files are all in there. So I've shown how what happens when the source circle is very small. What this does is it gives an indication of how the lens is distributed in the pupil or at the stop. And the next thing I'm going to do is show you what you do if you want to mimic it for a larger source. Okay, so let's say I set to 2 millimeters. What happens is it starts to broaden out a little bit because it's no longer a point source. So the various Gaussian apodizations from each of the point sources are then overlapped. So when we run this with a field of, the field size is 2 millimeters. So the semi-field is only actually 1 millimeter. So what it's doing is it's taking a circle.ima file and extending it so it's larger in size, which in general is going to tend to broaden or blur the Gaussian illumination at the pupil a little bit. And we can see that if we sort of do this extremely, like we make this 5 millimeters, it tends to blur this out a little bit. So down to this is 0.004. Divide. It's starting to blur a little bit at the edges. It's not a real strong effect because the distance from the source to the object is so long. So the other thing we'd like to look at is, I'm going to knock this back down to something more reasonable. What I want to do is check what the total irradiance coming from the source is in this simulation. And what I want to do is move it to object 1, which I've placed just a little bit after the source. And I'm going to make the image size smaller. So what you see here is sort of a flat top. Okay, if I change this to a false color. So what it's done is taken the IMA file, put it over 2 millimeter diameter, and now we're looking at it at this plane over here. So at this distance from the object, there isn't really a chance for you to see the Gaussian apodization that occurs, right? What's happened is a bunch of these sources are all now stacked up on top of each other, and you just see this thing come out as a flat top. And that's again because I changed the surface to surface 1. This is just after the object. So here's sort of a better picture, hopefully, what's going on. Here's the case we did first. We had the point source. The IMA file was a point source. I made it 1 micron in size, and you saw this at the front of the lens. If we make this thing larger, we can actually see what the distribution is right after the object. But if we go further away, it's still going to be the Gaussian apodization, right? So in this case, we go back here. Go to the front of the lens. And you have this sort of blurred out Gaussian. You always got to remember that change the scalings and so forth to keep track of things. So in summary, we had the aperture type set to numerical aperture so that we could turn the telecentric on. We changed the apodization from 0 to 1 to 2 to see the effects. We used this option to get a little more quantitative effect or quantitative feel for what was going on. We have the circle.ima files that define that particular source. And to look at things in the first simple fashion, I make the source circle very small because I want to see a point source effect in the system. And then later on, you can extend the field size if you want to mimic an actual source.